So for the first one, it's CaCO, it's just KSP equals Ca2 plus times CO3 2 negative, because CaCO3 dissolves into Ca2 plus and CaCO3 2 negative. And carbonate is one of those polyatomic ions that like will not really dissolve, and so like further, like it's all held together by covalent bonds. It's very strongly bonded together, and so CO3 is kind of like its own entity, the same way that like SO4 2 negative is, or like phosphate PO4 3 negative. And so because of that, the KSP expression is just Ca2 plus times CO3 2 negative. If you did do it in like the S form, it would literally just be S squared, because these would both just have a value of S. Do you have any questions about that one? Does that make sense? I'm sorry if it was worded kind of confusingly. You didn't understand that it was just like asking for this. Does that make sense?
Yeah.
Okay.
Yes, it makes sense.
Okay, sounds good. Then for the next one is just like a molar solubility problem. So it was given, you were given the molar solubility and you needed to find the KSP value. So for Ag2SO3, Ag2SO3 dissolves into 2 silver ions and just one of the sulfite ions. And so the KSP expression is Ag squared, because you have that, because you have the stoichiometric coefficient of 2 in front of silver, it's squared. And then, but SO3 2 negative only has a coefficient of 1, so it's just raised to the first power. And so you have your molar solubility, which is your S value, equal to 1.55 times 10 to the negative 5th molar. And so because there's the coefficient of 2 in front of the Ag again, it's like the 2s squared times S, so it's really 4s cubed. And so you have to plug the 4s cubed, you have to plug the S value into here. And so the KSP value would be 1.48 times 10 to the negative 14th. So this one right here. Does that make sense? Do you have any questions about that one?
No, that makes sense.
Okay, sounds good. So this next one is just like more of like one of the like harder KSP problems on here, mostly because it's required doing it for 3 different ions and kind of being able to, or 3 different compounds, and being able to kind of like deduce which one has the smallest value of KSP. And so for each of these, you're given the molar solubility. So kind of like how you did for this last one, how you go back and like calculate KSP from molar solubility. It's the same concept here, but it's kind of confusing because you have like 3 different compounds that have 3 different formulas, but they also have different molar solubilities. So you have to calculate if they all have the same molar solubility, you would be able to determine just like from the like chemical formula what it was, but with different molar solubilities values, you like actually to calculate it out. And so for the first compound, you have well, for AX2, you have molar solubility of 2.25 times 10 to the negative 4th. And when that dissolves into A plus and 2x minus. And so 1 mole of that is going to dissociate into 1 mole of the A plus and 2 moles of the AX or the X minus ions. And so your KSP expression would be A times X squared. And just like the last one, how you had to do like 4s cubed, it's the same idea here. And so instead of doing 4s cubed in the solution here, they just have it like as S and then like S times 2 squared. And so when you should get a KSP value of AX2 of 4.56 times 10 to the negative 11th. For A2X, it is it's going to be A squared times X minus, because it's going to dissociate into 2A plus and 1X minus. And so it's the exact same like thing here. It's like the 4s cubed again. It's just this time it's the cation that has 2 as opposed to the anion for X2. And so for this one, then you have the solubility expression is still going to be the 4s cubed again. So you just have to plug in that 1.75 times 10 to the negative 4th value again, and you square it, and you cube it, and you have to multiply by 4 as well. And so you would get 2.14 times 10 to the negative 11th as your KSP value. And I guess the AX value isn't in here, but it's just the exact same thing. And you would get a KSP value of 1.82 times 10 to the negative eighth because you've only squared it, you haven't like cubed it. It's gonna be the smallest, or it'll be the largest out of all three values as opposed to AX2 and A2X. And so because AX2 has the smallest value out of AX2 and because A2X has the smallest molar solubility out of A2X and AX2, and it's the only ones where that really small value was cubed, so it's even like smaller. The A2X actually has the smallest KSP value, so it's A2X here. Do you have any questions about that one? It's kind of just doing the exact same thing that you had done for the last problem, just doing it 3 times and comparing them to one another. Are there any questions about that one?
No, that makes sense. I wasn't paying attention to the actual. I just thought I said AX. So I was moving too fast, but yeah, it makes sense.
No, I totally get that. I feel like these ones are, it's weird to think about when you have like the really small exponent, because it kind of like changes. I feel like intuitively you'd be like, oh, if you're cubing something, it's gonna be the largest as opposed to square. Yeah, I did the same thing when I got the problem wrong in our study group. I was like, oh, if you square root it, it'll be larger than if you cube root it, but it's like not the same anymore with these super small values. Okay, so if we go on to the next one, I think this is the last one of like the actual molar solubility. So you have just like what's the molar solubility of calcium hydroxide in a solution with a pH of 9. So this one's kind of a weird one because it's the common ion effect. So you have some OH minus already present. And so one thing that you have to figure out by yourself with this problem is that the formula for calcium hydroxide is CaOH2. And so when you like do your KSP, you're gonna have to like take into account that it's not just CaOH. But hopefully you've seen like calcium hydroxide or magnesium hydroxide often enough where you're able to determine that yourself. The other difficult part is making sure that you get the correct concentration of OH minus when you start off here. Because you're given a pH of 9, so you might have the first thought of like, oh, I'll just do 10 to the negative 9th, and that'll give me the concentration of OH, but that's actually a concentration of hydronium. So you have to either solve for the concentration of hydronium and then use your like KW to find your autoionization of water to find OH minus, or in the solution they did, they found like the POH and then went and found the OH minus concentration that you start off with. So you have an initial pH of 9, so your POH is going to be 14 minus 9, which gives you 5. And so to find your OH minus concentration, you would do 1 times 10 to the negative, or you would just do 10 raised to the negative pH. It'll give you an OH minus concentration of 10, or of 1 times 10 to the negative 5th molar. So when you're doing your ice table now, instead of starting off with a concentration of 0 of your 2 OH minus, you actually already have a concentration of 1 times 10 to the negative 5th. And so you'd add S still, just like you always have. You would add S to the calcium, but 2S to the OH minus because there's 2 hydroxide ions. And so you actually have like, you have S times 1.0 times 10 to the negative 5th plus 2S. But we're going to assume that S is really small. And so because of that, we're just going to do S times 1 times 10 to the negative 15th. Or sorry, 1 times 10 to the negative 5th. Sorry, squared, because you still have the OH minus is squared because of the stoichiometric coefficient. But you have to like actually solve the 2S here because it's so small. So you can just do the small K approximation. And so when you solve for your molar solubility, your S here, you just divide your KSP value by that 1 times 10 to the negative 5th value squared. And so you would get 5 times 10 to the negative 4th as your, or it would be 4.68 with sig figs, times 10 to the negative, or times 10 to the 4th moles per liter. So it would be this one. Do you have any questions about that one? It's just kind of like making sure you have the right concentration of OH minus to start off with.
Yeah, all good.
Okay.
I have just one question.
Yeah.
So when you do like to find the S, how come you don't, because I know like usually when you're doing these calculations, you do like the 2 Like if it's like 2s, you like multiply it by 2 and then also square it by 2.
Mhm.
And when we're trying to find the s, it's only squared by 2. So how come it's not multiplied by 2 as well?
So the idea is like if you like actually defined if you couldn't use your small x approximation, you'd have to do s and then it'd be like 1 times 10 to the negative fifth. And then it would be that plus 2s. So that would be like where your 2s, where you had to multiply and then square it as well. But the thing is like when you're adding the 2s and you're multiplying by 2 and then you're squaring it, the idea is that like in your ice table, when you have a calcium hydroxide, the CaOH, when it's dissolving, it's creating 2 OH minus moles for every mole of Ca2 plus that's produced. And so that's why you multiply it by 2, because like whatever value of calcium that's going to be produced, we're going to produce 2 times that of hydroxide. But like with your initial concentration, that's just how many ions there are in the solution. And so you don't have to multiply that by 2. If you were trying to figure out how much like more was going to dissociate, you need to multiply by 2, which is here. But because of small k approximation, we can just like rule out this term and just not have to include it. So we would just end up squaring. Does that make sense?
Yeah, no, that actually makes a lot more sense. Okay,
Okay.
thank you.
Okay, so these ones are, I still think they're kind of strange, but this kind of goes back to like the acids and bases and thinking about like when a salt dissolves, if it's going to be like acidic or basic or neutral. And so this is just that again. And so you'd have CaCO3. If you remember, barium hydroxide is a strong base. So Ba2 plus is just going to like hang out in the solution, like it would just make a neutral solution. It wouldn't do anything. But CO3 negative is a weak base. And so if it's a weak base because of like common ion effect, it's going to actually do better in an acidic solution where there's less OH minus as opposed to in pure water. And so for A, it'll be acidic. And then for B, because you have S2 negative serving as a weak, like H2S is a weak acid. And so its conjugate is going to still be a weak base. So the S2 negative will be a weak base. And so even though the Cu is going to be there, because you have the S2 negative, the S2 minus, it's still going to be more soluble in an acidic solution than in pure water because of the common ion effect. So when you're thinking about this with like, I know it's like hard to like project it onto so many things, but if you think about it in terms of like, okay, a water solution is going to have more OH minus than an acidic solution because an acidic solution is going to have more H3O plus. And then when you have one of these like weak bases with water, you're going to end up taking and forming. So you'd have HCO3 minus plus OH minus. And so when you put this in water, you already have more of this OH minus in the solution than in an acidic solution. And that's like the common ion effect, like how we solved for in your last problem with deciding or like figuring how much the solubility or how much of the solubility, like what the solubility was when you already had some hydroxide in there because you have a pH. It's the same concept here that you're going to have more hydroxide in a pure water solution than in an acidic solution. So the common ion effect is going to prevent this from dissociating as much because if it does dissociate, it's going to produce more OH minus, which is going to put it back to CO3 2 minus, which was going to exist as BaCO3. So that's where like the whole idea comes from. So that's why you have to like consider whether or not it's like a weak base or a weak acid. So for CuS, even though you have the Cu there, the copper, the S2 minus is still going to act as a weak base. And so it's still going to go through if it reacts with water, it's going to produce first it'll just be HS minus, and then it'll probably grab another proton eventually, but it would be HS minus, and then you'd have OH minus. So because of common ion effect, you'd want something that had less OH minus in it. And so you'd want it to be in an acidic solution, not in a pure water solution, and definitely not in a basic solution. But AgCl is just So Cl minus is the conjugate of HCl, which is a strong acid. So Cl minus is just going to hang out in the solution, like not do anything, because it's just like a spectator ion. But if you had AgOH, it would be a weak base. And so when you have the conjugate of this, it's going to be Ag plus, which is a weak acid. And so it would do better, or sorry. Yes, the weak acid, if you like went by like the Bronsted-Lowry definition, it's because it can be an electron acceptor. It would be it wouldn't be a Bronsted-Lowry definition. It would be like a Lewis acid if it could be an electron acceptor. And so don't have to worry about that much. Just think about that because it doesn't have a weak base, because this isn't a weak base. It'll be more soluble in water than it would be in an acidic solution. So C is water, and then same thing here for PbI2. If you had PbI2, you'd have 2I minus, and I is just the conjugate of HI, which is a strong acid. So the I's are just going to be spectators. They're just hanging out in the solution. They'll create a neutral solution. And so because of that, it'll be water, not an acidic solution that it's more soluble in. Does that make sense? Do you have any questions about any of that?
No, it makes sense to me.
Okay.
Wait, so like if it's if it's basic, then wouldn't it just be safe to say it would better be an acidic solution?
Yeah. Exactly.
Okay.
Yeah. So like you see like the CO3 to negative, that's a base. It's going to be acidic. You see the COS, it's going to be the base. It'll be acidic. Same with like if you ever have like if it ever asked about like how MgOH or something, MgOH2 or something would do in pure water versus an acidic solution, because of common ion effect, it's going to be still be way better in an acidic solution than in a pure water solution.
Got it. Okay.
Okay, so then the next question is looking at you have an RBCl solution, or no, sorry, you have a solution that currently has 0.0018 molar AgNO3, and you're trying to get Ag plus to precipitate. So I know that I talked about this in my study group that Bryce is in, but I'm not sure that I talked about it in here. Your KSP value is like the cusp of when you're gonna have precipitation. Because if you think about like your Q value, when Q is less than K, that means that your products are lower than your like if you have products over reactants, you have products over reactants, and you have your Q is less than K, that means that your products are lower than your K value. And so like your products are too low. And so you would dissolve more in order to get your products concentration higher, because in these kinds of solutions or these kinds of like problems, KSP, you don't even have like a reactant in your KSP expression because a solid doesn't go in there. And so for products, or like if you have a Q that's less than K, your products would want to increase in concentration to try to reach that K value. And so if you have Q less than K, you're gonna, that's like not less than sign, it's like a curve. If you have Q less than K, you're gonna dissolve more. If you have like Q equals K, if you're at your KSP value, that means that you're at equilibrium, everything's great. You're gonna keep moving in equal rates in your forwards and reverse reactions. But then if you have Q is greater than K, whenever Q is greater than K, you're going to start going back to your reactant because your product concentration is going to be too large. So you need to start forming some of your reactants to get this value lower. And so when you have your Q value greater than your K, you're going to form a precipitate. And so your K value is like the border between where you're going to precipitate and when you're not going to precipitate. So a lot of these problems, when it says like in order to cause or in order to start to precipitate, it really means like compare it to your KSP value, because the minute that you add like a milliliter more or like half a milliliter more than your KSP value, then you're going to start to form that precipitate so you can reach equilibrium again. And so in these problems, when they're asking you to do that, you just equate everything back to your K value. And so you have a solution that already has AgNO3, which is soluble. And because there's only 1 mole of Ag in every 1 mole of AgNO3, you're just going to produce 0.018 molar, 0.0018 molar Ag plus. And you're trying to figure out how much RBCl, which is only going to produce 1 mole of Cl minus, or Cl minus, sorry, because you're forming AgCl. How, like, because like 1 mole of this, whatever concentration you add of this is going to add exactly 1 mole of, or the same amount, the same molar amount of Cl minus. And so it's really asking you like how much Cl minus do you need if you have this concentration of Ag plus in order to reach this KSP value. And so AgCl isn't a super complicated like formula for KSP, because there's only 1 Ag plus and only 1 Cl minus. And so you'd want to have 0.0018, which is your concentration of Ag plus, multiplied by your Cl minus concentration, which is how much RBCl you're trying to add, equals your KSP value, which is 1.77 times 10 to the negative 10th. And so all you have to do is just divide this KSP value by your concentration of Ag plus, and you would get a Cl minus concentration of 9.83 times 10 to the negative 8th molar. And so because it's a 1-to-1 molar ratio, whatever you have of Cl minus, you'd need that of RBCl. And so you would need 9.83 times 10 to the negative 8th molar of RBCl to get 0.0018 molar AgNO3 to precipitate. So it would be this one.
I have a question.
Yeah, go ahead.
Sorry. So I think I was a bit confused because first was AgNO3. How does it become AgCl? Like, how do you do? Can you just do that? Like,
so AgNO3 is aqueous. It's like one of those. If you remember like your solubility rules that you learned at the end of last semester, it's one of the aqueous solutions is going to form Ag plus and NO3 minus. So pretty much anything bonded to NO3 minus is going to be soluble. So a lot of times you'll see that where you'll see them add in like, I don't know, something either bonded to sodium or like potassium, one of those in the first row, or like bonded to Cl minus or NO3, things like that, because those are often the ones that precipitate out. And so if you have AgNO3 and you have RBCl, you're going to produce Ag plus because it's aqueous, and then RBCl is also aqueous because of the rubidium, and so it'll produce the Cl minus, and then NO3 is like pretty much always aqueous, so it's not going to form anything with the Rb plus. It'll just form with the Cl minus and the Ag are going to end up creating a precipitate. But it really goes back to the solubility rules that you learned at like the end of last semester. I would think that it would tell you like KSP of AgCl is whatever on the exam, but I couldn't guarantee that. That's how I figured, like that's how I think about it though.
All right, that makes sense.
Yeah. If anything's bonded to like sodium, like any of the things in the first row of the periodic table or bonded to NO3, you can pretty safely assume that it's just going to dissolve, and so you really just want the cation. And then if anything in the first column, you can pretty much just assume that you want the anion from that. Okay. So for the next one here, you would want to use, so for the next one, you're trying to find your equilibrium constant for this reaction. So it's PbCl2 plus 3OH minus yields PbOH3 and 2Cl minus, 2Cl minus. And so what you want to think about here is you have a KSP and you have a KF value. What you're trying to do is use those two KSP, those KF values to create this expression here. So your KSP expression is going to be this expression right here. It's your PbCl2 going to Pb2 plus and Cl and 2Cl minus. And then on the flip side of that, you have a Kf expression for this PbOH3 negative value. And so that one is going to be the Pb2 plus 3OH minus yields PbOH3 negative aqueous. And so you have these two values and you have these two expressions, and you add those expressions together, you can cancel out your Pb2 plus because it's the same on both sides of the equation here. But you're left with PbCl2 plus 3OH minus yields PbOH3 minus plus 2Cl minus, which is the exact same as this reaction that you have up here. And so because of that, your K value is going to be the two values added together. So if you remember, like, or sorry, not added together, multiplied together. If you remember, like when you add equations, you have to multiply K values because when you think about your K expressions, they're really fractions, and you can't really, like, in order to get to combine fractions, if they don't have common denominators, you really would be multiplying them in order to get them to like equal what your ultimate expression, like equilibrium expression was for this. So like, for example, your K for this would be K equals the PbOH3 minus times 2Cl or Cl minus squared. And that would go over PbCl, or sorry, PbCl2 would not be in it because it's a solid, but you'd have the OH3. So you'd have OH cubed. And so that would be your K expression that you want for this expression. But for your KSP value, it would be KSP equals Pb2 plus times and 2Cl, so it would be Cl minus squared. And then for your Kf, it would be the products of a reactant, so it'll be your PbOH3 minus over your Pb2 plus. And your OH3 minus. And so, or OH minus 3. So if you like want to combine these two K expressions to get this K expression, you wouldn't be adding them or subtracting or dividing anything. You'd be multiplying, because if you multiply these two expressions, you get the Cl minus in the numerator, as well as the PbOH3 minus. You would cancel out the Pb2 plus in the numerator with that one in the denominator, and then you'd just be left with the OH minus in the denominator. So that's why you multiply these K values together. So once you know how to do that, it's just a pretty straightforward, like multiplying these two K values that you're given. So you multiply that 1.17 times 10 to the 5th and 8 times 10 to the 13th, and you would get 9.36 times 10 to the 8th. Do you have any questions about that one?
So like the key thing here was probably just multiplying the KSP and the KF, right?
Yeah, exactly.
All right.
Okay, so this one's the last like K, SP, KF type of problem on this mock exam. But it's pretty involved because you're given concentrations of AgNO3 with NaCN, but it gives you the like milliliter, milliliters of those molar like values that are added together, and so it doesn't give you the total volume of the solution. So it's kind of it's kind of a long problem because you have to actually consider how many moles you're working with here. So when you look at the AgNO3, you have a volume of 120 milliliters, just 0.12 liters, not, I don't know why it says milliliters, it's 0.12 liters. And then same thing here, you'd have 0.10 NaCN, and then you'd have 22.5 or 22 5 milliliters of it, so it would be 0.225 liters of NaCN. And so in order to calculate the concentration of Ag plus in the solution, you have to use the total volume here. So you're given, you have to find the number of moles first. So when they're doing the 2.8 times 10 to the -3 molar times 120 milliliters, they're actually solving for the the total number of moles and then dividing by the total volume to get the new molarity of it. So when you find the new molarities of these two, you would get 9.73 times 10 to the negative fourth for Ag plus, and you do the same thing here, and you get 0.0652 molar for Cn minus. And so those are really the concentrations that you have to be working with here. And so you would then have this balanced equation. So you're told in the expression that you, like in the question, that your complex ion is AgCN2 minus. And I think they'd always give you these kinds of like compounds because they're very strange and they still have, like, this one has a charge on it, as you can see. So it's not just like, for the KSP ones, they just balance each other out to have a charge of 0. But for these ones, it's like, it can be weird. So I think they would always give you the value. I can't guarantee it, but I really think they'd always give you the complex ion that they're forming. So you're told what the complex ion is already. So you know that because it's AgCN2, that you would need 2 Cn minus for every 1 Ag plus. And again, Cn minus is cyanide is one of those. It's like how we saw CO3, how we saw carbonate earlier, or how we talked about like sulfate or sulfite. It sticks together and it's not going to dissolve further. And so you'd have 2 Cn minus and you only have 1 silver ion. And so when you start off with your concentrations here, you had to solve for your new concentrations of Ag plus and of Cn minus. So you have this N 9.73 times 10 to the negative fourth molar, and you have this 0.0652 molar of Cn minus, but you still don't have any concentration of AgCN2, so it's just a 0 there. And so you have to determine what the limiting reactant is here. So which value is the limiting reactant, the silver or the cyanide? Out of these two, you have a concentration of 9.73 times 10 to the negative fourth of Ag plus, and you have 0.0625, or sorry, 0.0652 molar of Cn minus, but you do need 2 of those. But which one's the limiting reactant? Is it the silver or is it the cyanide in this case?
The silver.
Yeah, because the concentration's so small, even though you need 2 Cn minus for every 1 mole of silver, you still have way more cyanide than you do silver. And so you would go to pretty much completion here. And so you would say, okay, I'm going to subtract around 9.73 times 10 to the negative fourth, and you're going to add about 2 of that, or 2 times that value, because for every 1 mole of Ag plus, you need 2 moles of Cn minus in order to create this. And so you would do 2 times this value and subtract that because it's how much you're using up to create the complex ion. But because you're only forming 1 mole of complex ion, you would just add just 9.73 times 10 to the negative fourth. And so instead of being 0 here, it's actually an X because you're in your expression for your KF. Let's see if it's written here. You still have Ag plus a part of it. And so if you had your concentration go to 0, your KF value would go to infinity. So it can't actually be 0. It has to be really close to 0. So when you're looking at solving for the concentration of silver, it wouldn't be 0 that remained. You'd have to actually do the calculation. And so you, for your total volumes here, you just do 9.73 times 10 to the fourth molar of your AgCN2 minus, and you have your, once you subtract the 9.73 times 10 to the negative fourth from this, it doesn't even like impact how much cyanide there is because it's just small value. And so you would square that because there's 2 moles of cyanide for every 1 mole of silver and every 1 mole of AgCN2. And so, oh, sorry, you would have to, in order to solve for KF, you would have to, you would divide 9.73 times 10 to the negative fourth. You would divide that by this 1.21, sorry, 1 times 10 to the negative 21st, or 1 times 10 to the 21st by this 0.0652 squared value. And that would give you your X. And so your X should be 2.3 times 10 to the negative 22nd molar. And so you would get this. You get 2.3 times 10 to the negative 22nd. If you got 2.3 times 10 to the negative 23rd, I think that one is if you didn't calculate new values, like new concentrations with the total volume here. So if you got this one wrong, but you got this one, that's what you did wrong. So a pretty simple mistake, just to keep that in mind. Any questions about that one? Does that make sense? Do you have any questions about that?
No, it makes sense.
Okay. So now we're going to get into like entropy and delta G and all of that. And so for this one, you have two systems, and you have each of them is composed of 3 like particles, and you have system A only has like 1 energy level that they're sitting at, but system B has 3 different energy levels that they're sitting at. And so because you could have, and like system A, you can only have them on this one line, and so it gives you only those positions for those particles to be in, because they can only be at 1 energy level. But in system B, you have the same number of total energy here. You still have 30 moles or 30 joules of energy here, but you can switch around the microstates of where these particles are going to go. So you could have the blue one going to 12 joules and the red one going to 10 joules. You have the red one going to 8 joules and the blue one going to 12 joules and the green one going to 10 joules. So you could switch all these particles around and have them be in a bunch of different positions. There's a bunch of different like ways for them to be to move around within this energy system, as opposed to system A. So system B actually has the higher entropy out of the two systems. Does that make sense? Do you have any questions about that one?
So basically, because like there's like, because entropy means greater dispersion, right? So
Yeah.
because like they're separated like that, that means when that's like a good way of to tell, right?
Yeah, I think that, well, it's like greater chaos and greater dispersion. So yeah, so I guess because they're more separated, it gives them a different number of and then maybe the better way to think of it is like how they could go into different positions. So less about them like being far apart from each other and more about them having like different places to go to.
Oh gosh. Okay, yeah, that's a way better way to memorize. All right, thank you.
Okay. So for the next one here, we have to determine the sign of delta S for each of the following chemical equations. So if you remember that the like delta S, I think you guys did a problem with this in lecture recently, where you had to just predict the sign of delta S and the sign for delta H. So this is just like kind of the delta S prediction here. But you have to consider how many the number of moles of gas on each side in particular, or like, I guess really just the phase of the particles and how they change, because you want them to be in a phase that has more like chaos and more movement, as opposed to like being in a solid state, for example. But the when you have everything like in a gaseous form, the way to determine it then is then to look at how many moles of gas you have on each side, because the greater number of moles that you have, the greater number of interactions that the particles are going to have, the like greater different like number of states the particles could go into, and like different like positions they could go into, because you would have more number of like a greater number of moles to change around what you are working with. And so in this first one here, you'd have 2 H2S, which is a gas, and 3 O2 going to 2 H2O gas and 2 SO2 gas. And so everything is gaseous here. So you can't like do like for the second one, we're going to look at state changes, but this one, everything is gaseous. And so what we're really looking at here is number of moles of gas. So on this side, you have 5 moles of gas, but on this side, you have 4 moles of gas. And so as the reaction proceeds, you're actually going to have less entropy because you're forming a fewer number of moles. And so because of that, your delta S, the first for A here, is negative. But for B, you're going from a solid to aqueous. And so when you have aqueous particles, that means that like they're in water. So you have to consider that like when you have particles that are aqueous, they're able to move around a lot more and they're interacting with water, as opposed to just like being held very rigidly in a solid and not interacting with any other particles. And so because of that, B would have a positive entropy because there's way more chaos on this side of the equation than there is on the reactant side. And then pretty similarly to this first problem here for C, everything is gaseous, so it doesn't really help you to look at like state changes. It just helps you to look at like what number of moles that you have on each side. So you go from 2 SO3 on the reactant side to having 1 mole of oxygen and then 2 moles of SO2. And so because you're forming 3 moles of gas as opposed to 2 moles of gas, you're gonna have you're gonna be going towards a state that has more entropy. So your entropy, your delta S is positive for C. Do you guys have any questions about that one, or does that make sense and everything? Okay, hopefully that makes sense. If it doesn't make sense, we can go over it again for sure, because I want to make sure that you feel totally good about entropy and everything. Does this make sense? Do you guys feel good about this, or do you want to go over it anymore? Do you have any questions?
No, it makes sense to me.
Okay. So now I'll kind of bring in like not only the delta S here, but also the delta H. So if you remember the reaction, that's like delta G equals delta H minus T delta S. Hopefully that reaction or that equation looks familiar to you. That's really the equation that you're going to be using to base what temperature is this will be spontaneous at. And so for this one, for example, we can look at how, if it's going to have a delta S that's positive or negative. But we're going from 3 moles of gas to 2 moles of gas. And so delta S is going to be negative here because you're going to a lower number of moles here of gas. But your delta H is negative already. And so your delta H is going to be negative already here. So you need, or I guess first we should establish that in order for a reaction to be spontaneous, you want delta G to be negative. If delta G is positive, it'll be spontaneous. And so your value for delta H here is negative already because you're told it's negative. But your value for delta S is negative. So you might be like, oh, they're both negative, we should be good. But if you have the subtraction sign here, it's actually going to turn, these two are going to turn into a positive value. And so you have to consider how large your temperature is, where if this value gets really, really large, it's going to be so positive that it outweighs the negative of the delta H, and your delta G will be positive. So you want to keep this value pretty low in order to make sure that you maintain this negativity to have a spontaneous reaction. And so this one will be spontaneous only at low temperatures to keep this value pretty small. So A is spontaneous at low temperatures. For the next one here, you have 2 NO2 gas going to 2 moles of NO and 1 mole of O2. And so your delta S is positive. But your delta H here is positive as well. So you have positive delta H and you have positive delta S, but you're subtracting this. So what you really want is that you want this expression, this T delta S value, to be really, really large, so that it's so negative, it outweighs the delta H that's positive, and it gives you a delta G that's negative. So the only way to get this value really, really large is to have a really high temperature. And so in order to be spontaneous, you have to be at high temperatures for B. For the next one here, for C, we have 2H2 plus O2 yields 2H2O. And so delta S is going to be negative because you're going from 3 moles of gas to only 2 moles of gas. So delta S is negative. Oops. So delta S is negative here, and your delta H is negative as well. So this kind of goes back to the exact same thing as the first situation here. You have a negative delta H, but you have a positive, or sorry, you have a negative delta S as well. So the negative delta S is going to make this whole value positive because negative times negative will be a positive. And so you would need to keep this at really low temperatures, so that this value that's going to end up being positive stays really small, that doesn't outweigh the negativity of delta H in order to be spontaneous. And so it'll only be spontaneous at low temperatures for C. And then finally, for D here, we have CO2 goes to carbon, which is solid, and O2. So your delta S value is going to be negative because even though you have 1 mole of gas on this side and 1 mole of gas on this side. Because you have the C as a solid here, it's actually going to make your delta S negative because the particles are going, instead of like being all gas, now some of them are gas, but also an entire mole of them are solids, which are like super organized, super not a lot of energy, not chaotic at all. And so your delta S actually is negative here because the change in entropy goes down. But your delta H value is positive. And so your delta H is positive, delta S is negative. This is going to be a negative times a negative. It's going to end up equaling a positive. So no matter what, delta G is going to be positive. And because of that, it doesn't matter what temperature it is, it's never going to be spontaneous. It's always a non-spontaneous reaction. And that should make sense because like in our atmosphere, it's not like the CO2 that's released into the atmosphere just creates, carbon and oxygen. So you can always think about like that kind of stuff as well to think about what makes sense and what doesn't.
I have one question.
Yeah.
So like when it goes into when it involves phase changes, so like as you go from a gas to a solid, it's safe to say then that it's always so it'd be non-spontaneous. Rather, if you went from a solid to a wait, no, do I think that's wrong? Yeah, it'd be non-spontaneous. If you went from a solid to a gas, that'd be spontaneous.
At least like entropy wise, yes. I'm sure there's
Yeah.
like some example where like the enthalpy is really weird or something, but entropy wise, yeah, that's exactly the right way to think about it.
All right, thank you.
All right, so for this next one, let me clear all of this. So for this next one here, we're trying to calculate delta S surroundings for this reaction. And so we're at 77 degrees Kelvin and we have a delta H of negative 385 kilojoules. And so let me annotate. And so this one, it comes from the delta G like expression, but if you just remember this equation, that's all you need to use. So you have the delta S surroundings is negative delta H of reaction divided by temperature. So once you know this reaction is, or once you know to use this equation, it should be a pretty straightforward calculation. It's just doing the delta H divided by the temperature. The only thing to consider is that delta S is generally measured in joules, whereas delta H is generally measured in kilojoules. And so at the end of it here, it is multiplied by 10 to the third to get it into joules again. But that should be reflected in the labels of the answer choices as well. And so when you do negative 385 divided by 77, you should get, it's like negative 385 divided by 77. So it'll give you 5 times 10 to the third joules per Kelvin. And so the correct answer is going to be 5 times 10 to the third. Are there any questions about that one? I feel like there's a lot of like little equations to keep in mind with delta G. So if you haven't done so already, I think that the like chemistry textbook might already have it at the end of the chapter. With all of the equations, let me see. Yes, like a lot of times the textbook, if you have the PDF of it, or I guess even if you have the actual physical textbook, it gives you like a lot of the laws and like the key relationships at the end here. So you can see like change in entropy of the systems. It gives you the expression here. If you don't have a little handout like this already, it might be good to like screenshot this and keep it on hand for tomorrow, or print it out or write it by hand so that you have it like as of ready tomorrow to be able to use. So if you don't have this delta S surroundings equation, it makes it like so hard to even know what you're working with. But with this equation, it makes it pretty straightforward to know what you have to do. So that one's just 5 times 10 to the third joules per Kelvin. Any questions about that one at all? Okay. Do you guys have access to the textbook? Would it be helpful if I just screenshotted that and posted that on Canvas, or did you guys like already have this? Is it good?
I have the PDF version of the test.
Yeah, I got it.
Okay, sounds good. Okay, so for 14 now, right? This one. Oh, sorry. They're like numbered weird on this one because we have the weird question in the beginning about true false, just to like keep attendance. So for delta H reaction here, we're just given the delta H, we're given the delta S value, and we're given the temperature, and we're supposed to figure out what delta S universe is. And then it's like, is the reaction spontaneous or not? And so this kind of goes back to the relationship between delta S of the universe and its relationship to delta G. And so you're given the enthalpy of the reaction, you're already given the delta S of the reaction, and you're given the temperature as well. So first you can use, so the ultimate equation that you want to end up using is the like delta S of surroundings equals delta H divided by T. And so first to convert your delta, you to convert your delta H into joules because it's in kilojoules right now, and everything's for delta S is usually measured in joules. And so you have to multiply by 1,000 and then just divide by the temperature to follow this delta S surroundings equation. So you would get negative 386 times, or sorry, you get negative 386 joules per Kelvin. And then because you have the delta S, the system as negative 263, which is just given to you in the expression here, you're able to do the delta S of the universe is just the value of the delta S of surroundings plus the delta S of the system. And so when you multiply or you add these two values together, you get a very negative value for delta S of universe is negative 649 joules per Kelvin. And so when you have a negative value for your entropy, that means that you're getting more ordered for your universe here. And so that's like the opposite of what you want to happen. If the universe is getting more ordered, it's going to be a non-spontaneous reaction. So because your delta S universe is negative, your reaction will be non-spontaneous. So it would be negative 649 joules per Kelvin, non-spontaneous would be the answer. Do you have any questions about that one? I feel like this is another one where like if you don't know the equation, it's hard to determine, but like once you know what you have to do in terms of which equations to use, the calculation part isn't so complicated. Any questions about that though? Does that make sense and everything? I think again, like all of those reactions, if you go back here, you have your delta S universe is delta S system plus delta S surroundings. And you can get your delta S surroundings using the delta H of your system. So, and does it make sense why if entropy of universe is negative, why your reaction would be non-spontaneous? Does that make sense?
Yeah, that makes sense.
Okay, and so if you get a positive delta S universe, then your reaction will be spontaneous. I think you guys did did like an activity like that in recitation one day. For this next one here, we're trying to actually calculate free energy now. So we're trying to calculate Gibbs free energy, the change in Gibbs free energy for a reaction, which is 2Ca plus O2 yields 2CaO. And we are given a delta H of the reaction, and we're given a delta S of the reaction. And we're asked, is this reaction spontaneous or not? I'm not sure if this, oh, here it is right here. And so for this one, we should calculate delta H, then determine whether or not it's, or delta G, and then calculate whether or not it's spontaneous. So for this one, we can just straight up use our delta G equals delta H minus T delta S. And so we're given our delta G already. This one, instead of converting from joules or from kilojoules into joules, they converted from joules into kilojoules. And then again, that should be reflected in like the answer choices here. So in order to convert from joules into kilojoules, you divide by 1,000, but you can just multiply by this temperature that's already given to you in Kelvin. And so, oh, sorry, I guess it's given to you at 25 degrees Celsius, but you would add 273 to it to get 298, and just a standard condition. And so you would do, plug everything into this delta G equation, and you would get a delta G equals negative 1,161 kilojoules. And because your delta G is spontaneous, that means that your delta S of your universe is positive, which means things are going like getting more chaotic. And so it will be spontaneous. Your delta G value is negative 1,161 kilojoules, and the reaction is spontaneous. Are there any questions about that?
No question.
This next one was more of like a conceptual question, just asking you how molar entropy, I guess the next several problems are really all about like molar entropy. So asking how the molar entropy of a system changes with when you increase temperature. And the answer to that one is that it increases, and hopefully it's like kind of intuitive to you at this point, because like as things increase, as temperature is increasing, your particles get more energy, they can move around more, can behave more randomly, you can go into different, you have more energy, so people go into different microstates. And so because of that, your molar entropy will increase as you increase the temperature. Are there any questions about that one? Does that make sense?
Yeah, it makes sense.
Yeah.
Okay, sounds good. So this next one here is another like molar entropy one. And we have to figure out the higher standard molar entropy. So molar entropy, the difference between like molar entropy and like entropy in an equation is just like the scale that you're working on. So when you're talking about molar entropy, you're really looking at these on a molecular level and how they have different entropy even on a molecular level. And so some of the rules about, do you remember any of like the changes, like differences that will cause something to have a higher molar entropy? Do you remember any of them? Like what kind of things cause a higher molar entropy?
I personally forgot.
That's okay. Do you remember anything, Kelly?
Is it mass?
Yeah, molar mass is definitely, oh yeah. And Paolo just had one too. Yeah, so molar mass is a perfect one. And then Paolo also just said gas. So like, yeah, when you have the phase changes, so first, if you have a molar mass, it means you have like a more complex molecule, you have way more atoms and everything in there, and so it's going to get more complicated and have a higher molar mass, which will cause more molar entropy because the electrons in particular can go into different energy levels and stuff. And then just like how this is in the chat, gas, because you have like a phase change as you get into a more like complicated phase, like state, like state, like phase, like solid, mole, solid, liquid, gas, aqueous, you're going to get like you're going to increase entropy because at the gaseous level they'll have more energy, more like space to move and everything, more interactions that are happening, as opposed to like in a solid everything's very ordered. And then similarly, if you have like an aqueous solution as opposed to just like an ion or just a solid, an aqueous will have interactions with water as well, and so that is going to really complicate things as well. So those are the two like main ones where it's like greater molar mass or like greater complexity. I think they kind of go hand in hand. And then also this like this state change. That was good that you guys remembered that. So this first one here we have NaNO3 versus we have NaNO3 solid versus NaNO3 aqueous. And so because of this one, you'd end up having NaNO3 aqueous having the higher standard molar entropy because the NaNO3 aqueous is gonna, when you have it has the aqueous, that means it's able to interact with water as well. So it's gonna end up dissociating into Na plus and NO3 minus. They're gonna interact with water. If you ever see a solid compared to an aqueous, the aqueous is gonna be more, have more entropy. Pretty much the same thing for this next one here. We have Br2 liquid versus Br2 gas. And so that gaseous phase is gonna have way more energy to be like way more chaotic, way more random than the liquid phase. And so Br2 is going to have the higher standard molar entropy out of these two. But then as you get to C, it gets a little more like confusing. And so it goes like to what Kelly had just said about molar mass. And so when you have Br2, which is the periodic table, your Br2, the mass of bromine is larger than the mass of fluorine. And so it's gonna end up having a larger molar mass than fluorine, and it's gonna have way more electron shells and everything too. So those like electrons have way more positions to move, they can switch around. And so there's way more like randomness and chaotic behavior in the Br2 gaseous than there is in fluorine too. or fluoride. And then for this next one here, you have CH3, CH2, CH2, CH3 gas versus SO2. And so for this one, you have so much more complexity in this, like this massive molecule. There's like a billion ways that electrons can move. It's super complicated, as opposed to SO2 is just like a sulfur and two oxygens. And so because of this one, you're gonna have way more complexity in this gigantic molecule. And so in D, this value, this CH3, CH2, CH2, CH3 is going to be your more, is going to have more standard molar entropy. And the same thing applies here with CH4. You have CH4 and they have CH3, CH3. So you could either apply like the greater molar mass or the greater complexity here. Either way, it's going to end up being much more complex as CH3, CH3 as opposed to CH4. And so this one.
I'm sorry, what do you mean with greater complexity?
So greater complexity, so I'm thinking that like, if you have, for example, you might have like some really heavy molecule, right? Like, let me pull up the periodic table.
Like a longer chain, right?
What'd you say?
Like a longer carbon chain or something like that?
Yeah, and so you would have like a really heavy molecule, like, I don't know how heavy like lead is, but lead, like even if you had like PbCl, for example, like PbCl2, I'll say PbCl2 aqueous versus, and I'm not sure if this one is aqueous, but let's say that it is, okay, versus like the CH3, CH2, CH2, CH3. So usually it goes hand in hand with like molar mass, but it doesn't always do that. So like PbCl2 might have like a massive molar mass, but it's just like one lead bonded to two chlorines, as opposed to like this massive molecule that has like a bunch of carbons and everything. And so there's a lot more, like there's a lot of movement for like the hydrogens to be able to move around and to have the electrons move around and stuff, because even though like you're told that things kind of look like a certain, like you might like, you know, if you actually do this out, you would be like, okay, it has CH3, so it'd be like C bonded to H bonded to H. In like the real world, the molecules don't really like stay totally in place like that, and like the H's are going to move around a little bit, so like this H might switch place with this H, and stuff like that. And so when you have these really complex molecules, they might not necessarily be heavier than like PbCl2, but they're way more complex. And so because of that, this one would be the more, this would have more standard molar entropy. But I think for all of these, it should just also be the greater molar mass. So let me see if like molar mass, SO2, that's what it was, right? So the molar mass of SO2 is just 64, and then you have this one is going to have a much higher molar mass than that. I think it'll be, I'm actually not sure, so let's see if it's like CH2. This is actually a good example of it. So this one has a molar mass. The SO2 has a higher molar mass than this one, this huge molecule. But this molecule is like so much more complex. There's so much more like many different ways for the different particles to bump into this molecule, for this molecule to kind of like change position and change shapes and stuff like that. And so because of that, it has some greater complexity. It'll be end up having a much higher standard molar entropy as opposed to the SO2, even though SO2 has a higher molar mass. Does that make sense?
Yes.
Okay.
It's like what Bryce said with like more chains and stuff.
Yeah, it's like you have pretty much, if you have like one of these crazy long like carbon chains, that'll be that'll have higher molar entropy because it's just like so big.
Okay, thank you.
Okay, so and then you kind of get to like test. So I guess are there any? That's a really good question. Are there any other questions about any of these other ones for this problem? Okay, if not, then we'll move on to the next one, which is like basically practicing this again. And so for this one, you're trying to rank the following substances in order of increasing standard molar entropy. And so for this one, the way that they did it, and it works because the complex molecule is also the heaviest, but if you had maybe something that was a little bit heavier, it might, so I guess actually you actually do have this here. So let me show you. So the molar masses for all of these helps you get started for organizing them. So for example, like He and Ne are really easy to compare to each other because they're both just one atom like hanging out. So they're really easy to compare to each other. And because of that, like He definitely has a smaller standard molar entropy than Ne. So that's how you can get started. Like they have the smallest number of moles, but so He would be the lowest, and that should be pretty easy to figure out. Okay, He is the lowest as it's only one atom and it has the smallest number of moles. But it might start to get tricky even with Ne, with neon, and with NH3. So this kind of goes back when you have to compare these two. You have to think about, okay, not only do I have molar mass to consider here, but I have to consider like complexity here because NH3 has three different it has like 4 atoms as opposed to neon having literally just being one atom. And so because of that, even though NH3 has a smaller molar mass than neon, it actually is more, it actually has more standard molar entropy. And so because these two are comparable just because of size, but actually the neon is less than the NH3. So you would have He first, then Ne next. Then you have to consider, okay, is it going to be neon or is it going to be the sulfite here? But the sulfite still has less complexity because it has a fewer number of like atoms involved in this molecule here. It only has 3, whereas the NH3 has 4. So even though it has a molar mass of 64, it's still like less atoms than NH3 is. And so it actually, SO2 actually has a smaller molar entropy than NH3. So that's how you order the first ones. And then this last one here, you can also do the same thing where you count the number of like atoms involved in this molecule, and you'd have 1, 4, 5, 7, 8, 9. So you have 9 moles or 9 different types of atoms involved here, as opposed to only 4 here and 3 here, 1, 1. So this one is the most complex, definitely. And so that one has the highest standard molar entropy. Does that make sense? Any questions about that? So I would say look at the state first, look at like whether it's like a liquid versus a gas versus a solid, because like that's going to be the number one most important thing for determining molar entropy. And then I would count the number of atoms that are involved in that molecule. And so if it has a greater number of molecules, it's going to have greater complexity, or sorry, it has a greater number of atoms, it has more complexity, it'll be have more entropy. But if it has the same number of mole or same number of atoms, for example, like Ne and He, you can just compare their molar masses to determine which one comes first. And so that's why it is this order. Are there any questions about that one? So do this. Any questions? Okay, makes sense. Sounds good. Okay, so now we have to determine delta G for the reaction, and we're given delta G values for a different reaction. So I just left this as a true false for you guys. So for this one, you have 2 different reactions here. You have 2 FeS plus 3 1.5, so 3 halves O2 yields Fe2O3, and then you also have CO plus 1/2 O2 is CO, and you're given the delta G's for both of these reactions. And what you're trying to make ultimately is Fe2O3 solid plus 3 O2, sorry, plus 3 CO plus 2 Fe plus 3 CO2. And so, first what we have to do is that this first reaction, we wanted Fe2O3 as a reactant, and we currently have it a product. So first thing to do is to flip this reaction. So we're going to flip, we're going to reverse it. And then in addition, so if we're going to reverse it, we multiply by -1. If you remember like Hess's law from like December, this is the same concept here. So because you're going to flip it around, you're going to multiply by -1 because now we're going in the opposite direction. So it's going to be like the reverse reaction. So first thing you would do, you would flip it around, and then you only wanted 1 mole of Fe2O3, and you have 2 moles of Fe, and so we should be good as far as just like flipping this one around without having to do, without having to multiply by anything. But then for this one, we have 3CO going to 2Fe going to 2Fe and then 3CO2. So no, this is actually supposed to be CO2. If I just got lost in the copy and paste. And so trying to decide. So it says, let's see here. Yeah, so it should be CO2. And so for this one, we have the CO2 on the correct side here, but we need to multiply by 3 in order to get to have 3CO2 and 3CO. So for this one, we multiply by 3. And so, clear. So we have the reactions here. So we have to multiply this one by -1, and we have to multiply this one by 3. And so in order to get our final reaction here, we'd end up canceling out the 3 halves O2 that we would create on each side, because when you multiply this by -1, you're end up going to get the 3 O2 on this side. And when you multiply, when you multiply this one by 3, you're going to get 3 halves as opposed to 1 half. And when you multiply this by -1, you switch the sides of the O2. And so they'll end up being on opposite sides for you to cancel. And then you'll have everything on the correct sides for you. But now when you add these reactions up, you have to add their delta G values. So it's not like our K values to multiply, where you have to multiply, because for these ones, we're just adding the reactions. It's not like we're trying to find like a K expression where you're doing fractions. For these, you're just doing like delta G. And so delta G is just like delta H. You just add them together. And so your delta G of reaction is -29.4 kilojoules, which is true. Do you have any questions about that one? I'm sorry, I have to trip you up and said CO instead of CO2.
This is like Hess's law, right? Pretty much Hess's law.
Yeah, it's like, I then it might not be called Hess's law because it's delta G instead of delta H, but it's like literally the exact same thing.
Okay, thank you.
All right, so now we have some of the harder ones, I think, where we have to figure out delta G. These next two, we figure out delta G based on we have to use our Q and our K values. And so we're under non-standard conditions, so we can use, because we're already told. So do you remember what standard conditions are? If we were under standard conditions, what would our pressures be for each of these? Any thoughts?
Under standard conditions,
Yeah, what would our pressures be?
1 atm.
One.
Yeah, exactly. Perfect. Yeah, so if we were under standard conditions, everything would be under 1 atm, and then you would use a different reaction, and you'd use like the natural log of K type of reaction or of equation. But here we're not working under our standard conditions, we're working under non-standard conditions. So we're going to use our delta G equals delta G standard plus RT ln Q. And so we have to, so you're giving your delta G standard, you're already given that is 25.1 kilojoules. And you also have your R value, which is your rate constant, right? Your rate constant, sorry. Like it's just the constant, the 8.314 constant. And you're giving your temperature in degrees Celsius. So you have to convert it into Kelvin, but it's still under standard conditions. So it's that 298 Kelvin temperature that you guys see very often. But the real thing that you have to calculate here is that you're given 3 different pressures. And so you need to be calculating a Q value in order to plug into this equation to solve for your delta G. So if you remember this reaction, it's given to you. It's CH3OH going to CO2 plus 2H2. And so if you remember, our Q expression is just like our K expression, just not necessarily at equilibrium. And so it's our products over our reactants. So we have the pressure of carbon monoxide times the pressure of hydrogen, but it has to be squared because we have that stoichiometric coefficient of 2 in front of it. And then we put that over top of CH3OH because that's our reactant. So that's our Q expression. And now we have our pressures already. We can just plug into our equation here. So we would plug the pressure of carbon monoxide, we would multiply, or we would have to square the pressure of H2 first because of our stoichiometric coefficient. We'd multiply those two together and we would divide by the pressure of the CH3OH. And so when we do that, we get a Q value of 0.004896. So now we have our Q value. We were given our delta G standard. We were given our temperature in and we're given it in Celsius. So in order to convert to Kelvin, we had to add by 273. And the other thing to notice here is that usually your constant 8.314 is in joules per mole Kelvin. So because the answer choices were given to you in kilojoules, you had to make this conversion at some point in the reaction to go from joules to kilojoules. So in order to make the conversion here, you'd have to just multiply by 10 to the -3 in order to, or like divide by 1,000 in order to get it into kilojoules. And so that's what they did here when they have like the 8.314 times 10 to the -3, it's just getting it from joules to kilojoules. And so you would just plug into this reaction, you have your value for delta G standard, you have your value for your R, you have your T, and then you have your natural log of the Q value that you just calculated. And so your delta G of your reaction is 11.9 kilojoules. So hopefully that makes sense because, okay, so are we told what our K is? No. But hopefully this makes sense. And so if your reaction, if your delta G is 11.9 kilojoules, is your reaction going to be spontaneous or non-spontaneous?
Isn't it non-spontaneous?
Exactly, yeah, because it's positive delta G. So our reaction is non-spontaneous here. So does that mean that this reaction is going to precede the CH3OH? Does that mean it's going to go in this this direction, the forward direction? Or does it actually mean that it should probably be proceeding in the reverse reaction if this way is non-spontaneous?
But I'm sorry, can you say that one more time?
Sorry, could you repeat that?
I said, I'm sorry, can you say that one more time?
Yeah, so we're figured out now our delta G value is positive. So we said it's non-spontaneous because our delta G is positive. And so if the reaction is non-spontaneous, should it proceed in the forward direction or in the reverse direction?
Forward?
Yeah, it'll proceed in the reverse direction because if it's in the forward direction, it's non-spontaneous. So no, don't get worried about understanding it. Just think it through. If the reaction is non-spontaneous, it's not going to happen, right? And so if this reaction isn't going to happen, it'll actually go in the opposite direction because we're not equal. If we were at equilibrium, our delta G would be 0. It's not 0. It's not negative. So it's gonna have to go on the reverse way. Okay, so if we're going in the reverse direction, let's think about how we can compare our Q and K here. So we're trying to go in the reverse direction here. We have our Q value. Is our Q going to be less than K or greater than K if we're non-spontaneous right now?
Greater than K.
So if our Q is greater than K, we'd have products over reactants.
I'm gonna go find my little, what is this? There we go. I have a little post-it.
Yeah, if you have products over reactants, that's perfect. If you have products over reactants, then if you're trying to go in the reverse reaction, that means that your Q must be larger than your K because you need to be proceeding towards your reactants.
Yeah, so it will create. I don't know if this makes sense. So to create precipitate, I don't know if that makes sense.
So if CH3OH was a solid, you would be totally correct. Or if it was like a KSP expression, it would be towards a solid. It would definitely precipitate.
Yeah.
In this case, because we're working with gas, it will not precipitate. It'll just form more of this CH3OH. That's a good like thought to link it together with the KSP stuff.
Yeah, because I mean, I link it because last night we had a review session like for the test, and he said that you know how you have LNQ.
Yeah.
So he said that whenever we have a KSP and Q is given to us, you can just do like what is this? You can just replace LNQ for LNKSP. So and then you find delta G, and then you can go ahead and see. You know how do you call this? You can like expand the equation.
Okay.
Yeah, it's a little confusing because I'm still learning.
No, I know what you're saying. It like kind of makes sense, but I'm not quite sure either. But that makes sense, and I think that your ideas are totally right. Where if this instead of being like a QP here, if it was like a QK or QSP instead of a KSP, if it was a QSP, you'd be like 100% correct that we would form a precipitate here. The only thing that you're like a little bit off about here is just that we're not working with KSPs, we're just working with a normal K here. But if you're working with a QSP and a KSP expression, you'd be 100% correct. Are there any questions about this? I know like the Q and the K stuff is some of like I think it's probably in my opinion, it's the most confusing part of like all of this. So are there any questions before we go to the next problem? Okay, so we have CH, in the next reaction, we have CO2 going to 2H2, and that forms CH3OH. And so you were given like 3 different things to calculate delta G at. So you have to calculate it at standard conditions, at equilibrium, and then at a bunch of different pressures. So we'll start at standard conditions. So you guys already told me standard conditions mean that each of the pressures is 1. So if we're at standard conditions, what is our Q value? If each of the pressures is 1.
Q equals 1 as well?
Exactly, yeah. Perfect, because you would literally it'd be like 1 divided by 1 times 1 squared. So 1 is perfect. So whenever you know your standard conditions, your Q is going to equal 1 for KP or for QP. And so if you remember, what is natural log of 1? What does it go to?
0.
Exactly, right? So you'd have the reaction where you had like delta G equals delta G equals delta G, I think it's delta G standard. We like just used it. I always forget it. Delta G plus RT ln Q. I can never remember if it's a plus or minus. Plus RT ln Q. Oops. Horrible plus sign. But RT ln Q, and then if you had your ln Q go to 0 here, this whole term is going to go to 0, so this cancels out. So your delta G is going to end up equaling your delta G reaction, your delta G standard. And so you're already told that your KP, this is kind of like a confusing problem. So we've already determined that our delta G of our reaction equals a delta G standard. And so we're given our KP value here. So now we've determined this. Now we can go back to our delta G of our reaction here, that equation, and say delta G reaction equals negative RT ln K. So we use this first reaction, this first equation. Where is it? This equation, just like how you did in recitation like 2 weeks ago, maybe it was even this week. How you like determine that delta G equals delta G standard. We just did that again, so we know that delta G equals delta G standard. So now we can kind of switch our equations up. We've already determined that delta G is going to equal delta G standard. So we can use the delta G reaction to equal negative RT ln K. But we're given our K value, we're given our temperature, and we're given our constant. We know our constant already. So we can do delta G of reaction equals 8.314 times 298 Kelvin, and we're given our Kp value. And so it's 2.26 times 10 to the fourth. And so when we do this calculation, we'll end up getting negative 24,839 joules per mole, or negative 24.84 kilojoules per mole is more easily understandable. So our delta G under standard conditions is negative 24.84 kilojoules per mole. First, are there any questions about that one? I know it's like kind of like a lot of leaps to make, but does that make sense? I would say important things here that probably are going to come up again, because they're probably going to throw something on the exam where it's like, what is the delta? Like, what is the delta G under standard conditions? Because then you have to make that, you should know that the standard conditions are 1. And so just to reestablish that here, first you're using this equation. So this equation is used when you know you're not at equilibrium. So, or you don't know if you're at equilibrium. And so we're working with ln of Q here, because at standard conditions, it's like so rare to be at equilibrium and at standard conditions. Like, don't even consider it as a possibility in your mind, really, because in order for that to happen, your K value has to be 1, which is like, just does not really ever happen. And so when we have standard conditions, we're not working at equilibrium. And so we can use this reaction, that's delta G reaction equals delta G standard plus RT ln Q. But this RT ln Q is going to end up going to 0 because our Q value is going to be 1 because all of our pressures are 1. So this gets, I'm getting knocked out. So we now have our delta G equals delta G standard. And that should kind of make sense to you, because like delta G standard is the delta G at standard conditions here. So you could be like, okay, this is just my delta G at standard conditions. I'm working at standard conditions right now. But I think that it's easier to keep in mind then that you are also working, that you're not working at equilibrium right now. And so you can use delta G of your reaction then, you know, delta G of your reaction equals delta G standard of your reaction. So now it's like, okay, let's go plug delta G standard into this equation to figure out what this delta G is. And so you already have your R value, you had your T value, and you had your K value at equilibrium. You plugged it in here and you got a delta G reaction. So that's where like that kind of like line of thought comes from. It's really similar to the problem that you did in recitation a couple of weeks ago, or and literally might have been a week ago. I don't remember how long ago that was. So that's the first one. Are there any questions about that? Does that make sense? Was it easier this time around than it was in recitation, or is it still really hard to think about?
For me, I feel like it's still like a little confusing to think about.
Do you
But
want to
yeah, I
go?
guess-
Oh, sorry.
Oh yeah, what did you say?
Do you want to go through it again, or do you feel like you need to sit with it longer? Or like, would it be helpful to go through it again?
Yeah, maybe.
Okay. So first thing we have here is that we have standard conditions. And so we're told that. And so for standard conditions, that just means that like everything's at a pressure of 1 atm. And so our reaction, like our Q expression would theoretically be this like PCH3OH the equals over pressure of CO2 times pH2 squared. But the thing is that at standard conditions, literally everything here is equal to 1. So your Q value is going to be like Q equals 1 divided by 1 times 1 squared, which is just going to be 1. So your Q value is going to equal 1. That's what it's saying here. And then we know we do ln of 1. And so if you ever forget it, you can always just put it in your calculator. If you have ln of 1, it equals 0. And so you'd have this expression where you'd have delta G equals delta G standard plus RT ln Q. But the thing is that we just said that RT ln of Q, this is a T, sorry, RT ln of Q is equals to 0. And so if this is equal to 0, this whole term, because you'd be like, you do like 8.314 times 298 times 0, it just goes to 0. So now at standard conditions, we have delta G equals delta G standard. Okay, so now if we have delta G equals delta G standard, we can kind of go from there. So if delta G equals delta G standard, now let's use our delta G reaction equation instead of our delta G standard here, because we're trying to figure out delta G standard. And so for delta G reaction here, it equals negative RT ln K. But the thing is that we were given our equilibrium constant. And so we can just plug our equilibrium constant in here and then just get our new delta G value. And so that's exactly what they did here. We're given our KP value here. So we just plug that right in. We're given a temperature, just convert that to Kelvin instead of Celsius. And we have our constant already. So we just do delta G reaction, you multiply these three terms together, and you would get negative 24,839 joules per mole, or you could convert it to kilojoules because it's a really big number, and you would do 24.84 kilojoules per mole. So that's where it comes from. Does that make sense? Is it better this time around?
Yeah, that makes a little bit more sense.
Okay. Does anyone else have any questions about this, or why anything is what it is? Okay. So now for the next.
Wait, I have one question actually.
Yeah.
Sorry.
Okay.
Wait, so with all that, what was the point of needing the ln Q equals 0?
I think that like if you already had your let me pull up like the equation sheet. So if you have this equation here, and you have delta G equals delta G standard, I guess you don't have to know it, but I think that sometimes it's hard to just like remember which equation to use. So I guess if you wanted to, you could just like, okay, I'm at standard conditions, I'm going to use this equation, and you could just use that equation. But it helps to kind of create the relationship between this reaction or like this equation and equation.
Okay.
But I guess that's, yeah, you don't really need it.
No, that makes sense. All right, thank you.
Okay. That's a good question though, definitely. So for the next problem here, we're trying to do it at equilibrium. So we were given our Q value. And so we can do delta G equals delta G standard plus RT ln K. And so because we're not at standard conditions. And so usually you see it as RT ln Q, but if you remember that K is just like a special case of Q when you're at equilibrium. So your Q value here is just your K value because you're at equilibrium. And so you just do your delta G standard, which you already solved for in the first part of the equation here. So that's like your 24,000 value. And then so that's what you solve for up here. And then you have your 8.314 times your 298, and then times natural log of your God, sorry, my brain's not working, of your K value. Yeah. So then when you do all of that, you end up getting negative 24,839 joules plus 24,839.4 joules, and you end up getting 0 joules per mole. So ultimately for equilibrium reaction, you don't really have to do a calculation for this one either, because you could do the calculation and it works out. But another thing you can always keep in mind is that at equilibrium, your delta G is going to end up equaling 0. So that's something else you can remember as well. Does that make sense?
Yeah, I think so.
Okay. Any questions about this one? If you ever see problems like, what is your delta G at equilibrium? It's 0. It's always 0 at equilibrium. Okay. This next one here, this is like where it kind of goes back to what we had done in the last problem, when you weren't at equilibrium, but you also weren't at standard conditions here. So we're given pressures, we're given 1 atm for the CH3OH, 0.01 atm for the CO, and we're given 0.01 atm for the H2. And so we can plug them into, here's our Q expression still written out here. We can use our delta G reaction. So the equation they're using here is this one here, the delta G reaction equals delta G standard plus RT ln Q. So if you remember from part 1, you got your delta G standard because you did it at standard conditions. And so in order to calculate our delta G reaction, we have to plug in the RT ln of Q, but our Q isn't 1 anymore, and our Q also is not our K value. Our Q is like our special Q value at these pressures. So in order to calculate your Q expression, you would do what I did right here. So you would do, so you would do 1, which is the pressure of your CH3OH, and then do 0.01 times 0.01 squared, which is the pressures of your CO2 and your H2. And so when you do 1 divided by 0.01 times 0.01 squared, you end up getting 1 million as your Q value here. And so again, where everything comes from, this negative 24,000 value, it's in joules per mole Kelvin, and it is, or joules per mole, and that is your delta G standard. That's what you calculated for number 1 here. You calculate under standard conditions. That is from your, that is from your equation. That's the at standard conditions, delta G standard equals negative RT ln K. So that's like what that comes from. And this comes from, this is your Q value, and you're given your pressure, or sorry, you're given your temperature, and so you convert it to Kelvin, and you have your rate constant. And so you would do your delta G standard plus this new RT ln Q value, and then you would end up getting 9,389.5 joules per mole, which is just 9.39 kilojoules per mole. Does that make sense? Are there any questions about this one? I think that really the hard part of all of this is like keeping track of which equations you can use for different things, and kind of like keeping track of the difference between like just delta G of reaction versus delta G standard. So that's the entire mock exam. If you have questions about any problems, we can go over certain problems again, or we can go over something else if you guys wanted as well before we until 4 p.m. So what would you guys like to do? Would you guys want to go over anything else? Do we go over any of these problems again? How are you guys doing?
Wait, could you go back to that last problem, but the first, the standard conditions part?
Yeah, do you want to go over that again?
Oh, that's why. All right, so I was just confused because like in the third one, it was like use the joules per mole, not the kilojoules per mole. So
Yeah.
that threw me off a little bit. I thought it was a different number.
No, so it's just that the joules per mole, and that's because your rate you could use the kilojoules per mole. You would just have to change your constant to be in kilojoules per mole. So I think they just use the joules per mole to not have to do the conversion again.
Gotcha. Okay. All right, that makes sense. Also, could we by any chance go over the oxidation reduction stuff? Is that, I think that's going to be on the test, right?
Oh yeah, like the acid base oxidation.
Yeah. That.
But actually, okay. So this is like a preview into our study group tomorrow, I guess, Bryce, or on Tuesday. So sorry if it repeats. But yeah, we can do it. So basically, you are going to have to do this in like 2 different kinds of mediums. So you're either going to do it in an acidic medium or in a basic medium. And so the 2 differences here basically is that in an acidic medium, you are allowed to have H plus present, whereas in a basic medium, you'd be having OH minus present. And so if like, for example, you have to add H plus on the basic medium, you need to be converting that to OH to like H2O, and then really have it be OH minus on the other side of the reaction. And then kind of same thing goes for the acidic medium. If you need to be having H plus on one side, but it kind of naturally lends itself to having OH minus, you would need to be doing like converting it so that you'd have H2O on one side and H plus on the other side. And so we can go over, so this one's for acidic reactions, for example. And so for oxidation, if you remember, oxidation means that you are getting like more positive in charge, whereas reduction means you're getting like more negative. And sometimes it's like kind of hard to think about which way the electrons go and everything and which side of the reaction. But you basically want the sides to add up to having the other side of it. So whatever side you have a positive charge on, you want your electrons on that side. So if you have a positive charge, you want your electron on that side so that you have an overall charge of 0. And so for this first one, for example, let's go through it. So for what's being oxidized here, we'll see what thing is getting more positive. So Ks is going from a Ks that has a value of 0, so it is solid state, it has a value of 0 for the charge of it. And then it's going to K plus aqueous, it's going to become ionized. And so that means it's getting oxidized because it's becoming more positive. And so we can write our half equation first. So we'd have our K value, our K yields 1 electron plus K plus. And hopefully this makes some sense to you because it's like, okay, we have our K value and it's getting like, it's losing an electron in order to become K plus. So let's lose an electron and become K plus.
What's so confusing about this is because when you're like reducing, it actually means that it's gaining.
I know, it is so,
so it was like when I was in high school, I tried to see like does it complete opposite, but then when my teacher was explaining, I was like, oh my god, I'm about to give up.
it is confusing. I feel like this is probably, I know it's like kind of foolish, but like, because I know like on the surface, the stuff should not be that hard. But when I was in chem, I think that oxidized, like I remember on the quiz that I had to do redox reactions, I got like a bad grade on the quiz on it. I don't know why I had so much trouble on it because like looking back, it's like, it makes some sense, you know? But I think when you first learn it, it's like so not intuitive from what everything you've learned so far. It's like, if I'm being reduced, why am I gaining the electrons now? Like it's sort of confusing. So I think the way to think about it is that to really think about the charges and how they're changing. If it's oxidizing, it's going from positive or something for like a 0 charge or a negative charge and becoming more positive or less negative. So it really should be giving up electrons. So when it's oxidizing, it's getting rid of electrons. When it's reducing, you're reducing the charge. So you need more electrons to reduce that charge down. And so for the oxidizing side here, you'd have your K, which is your 0 charge. It loses an electron and it becomes positive. But when you reduce something, you have something that's really positive and you're like, let's add 3 electrons onto it. So it becomes less positive. The charge reduces from 3 plus to 0. And so you can look at these 2 reactions and you're like, okay, I have K yields 1 electron plus K plus. Okay, fine. And then I have reduction equals Cr3 plus 3E negative yields CRS. And you're like, okay, fine. But now what do you do in order to like actually like balance these equations? Well, you have 3 electrons in this one and only 1 electron here. So you actually have to multiply everything in this reaction by 3 in order to be able to cancel out the electrons from this side to the electrons on this side. So that's why your balanced equation for this one actually is 3K plus Cr 3 plus yields Cr solid plus 3K positive. Are there any questions about that?
Oh wait, never mind.
Okay. So those ones, like, they're kind of hard, but I think that where it gets really tricky is where you have to consider if you're in an acidic versus a basic medium. And so that's where like the hydrogens and the waters and stuff kind of come into. So I'm going to go down to C for this one now. So I guess first, are there any lasting questions on A? Do you feel like you're able to process it? Does it make sense why the balanced redox reaction is this? Any questions about that?
Wait, so you're adding 3 electrons to the, what is that, to the K? Is that what you're doing? I'm sorry, for the oxidation part. Oh wait, no, you're taking away. Sorry.
Yeah, so you're losing 3 electrons. That way your K is actually becoming more positive. So are there
I feel like the easiest thing to see is oxidation. You're gaining, so you see that K is going from, it doesn't have a charge and it's going to a positive charge. And then reduction is what is name of is reducing, so it will go from a positive charge to a negative charge. But then after you understand that, you have to acknowledge the reality of it. There's actually the positive means that you're actually taking away. Meanwhile, the negative means that you're adding. Exactly. But when it comes when it comes to like, if you see these equations and you just to like understand that, like the oxidation agent and stuff like that, then that you're good on that.
Exactly. That's what I that's what
Gotcha.
I had too. Yeah. Okay. So
All
now
right.
I'm gonna
I
go
think
down.
that.
Okay.
Wait. Actually, no. One more thing. So then,
Oh.
how come it's 3 and not 1 though? Because the K is a +1 charge,
Yeah.
not plus
So
3.
so at first it is, right? So at first when you wrote your oxidation reaction, you only had one electron that you're losing for every like one potassium. But when
Yeah.
you have your chromium, I think it's chromium, you have 3+, and then you've had to gain 3 electrons to go from charge of 3+ to 0.
Mhm.
So you need to be canceling, just like kind of like a normal like balanced reaction. You have 3 electrons on this side, you have to have 3 electrons on this side. Just like Hess's law, how you had to like multiply by 3 to get the same concentrations of whatever, the same values for moles of oxygen.
Oh, okay. Yeah,
And you
that's
multiply
true.
by 3 for the whole reaction here. So now you have three potassiums. Now each potassium is losing, you have 3 potassiums, each one loses 1 electron to become positive. So now you have 3 potassium ions that are positive, but they've each lost 1 electron, which gives you 3 total electrons. And now your electrons actually cancel out.
Got it. Okay, that makes sense.
Okay, so now we can look at like more of an example in like a positive solution, like an acidic solution. And so if it's an acidic solution, it'll have a lot of H+ in it. So we have this reaction here. We have a BrO3 negative plus N2H4 yields Br minus and N2. And so what we have here is that what you have to think about here is that we basically don't have any of the like H's or the O's on our product side here. So what we really need to be looking at is the charges of the N and of the Br. And so in this one here, you have an overall for BrO3, you have an overall charge of -1, but the oxygen are actually holding, if you remember, like oxygen have a charge of -2 each, and you have 3 of them. So you learned that like last semester when we talked about oxidation number. So oxygen has a charge of -2. There's 3 of them, which actually means it has a charge of -6. The molecule has an overall charge of -1, so it kind of is like, in order to balance out -6 plus whatever charge Br is holding equals -1, Br would have to have a charge of +5 in order to balance it out. So BrO3, the Br has a charge of +5, but on the other side it has a charge of -1. So Br is definitely being reduced, going from like a +5 to a -1. On the flip side, you have N2H4. And N2H4, each H has a value of +1, which again is one of those oxidation numbers you learned at the end of last semester. There's 4 of them, which means that you have a charge of +4 coming from the H's. In order to cancel it out, because you have an overall charge of 0 on this molecule, that means that the N must be holding a charge of -4 for oxidation number. And so because overall you have to add up to 0. And so the N is going from a charge of negative, the N2 is going from a charge of -4 to an N2 charge of 0. So that means it's actually being oxidized. So first, are there any questions about that? About determining which substance is being oxidized versus which substance is being reduced without looking at any of the equations yet? Does that make sense so far?
Yeah.
Okay. So now we know that, and we're like, okay, time to start looking at these reactions. So to figure out, we have N2H4 goes to N2, but it's not really like our full balanced equation here because we still need 4 protons on here. So let's throw on 4 H+ here. But the thing is that when you have, so there's 2 ways to think about it, I think. The first way you can think about it is that the N2 just went from a charge, as we figured out, the N2H4, if you remember how the hydrogens each have a charge of -1, so in total is holding a +4 charge, and the N2 has a charge of -4. So you can think of it that way, where the N2 has a charge of -4, it's now going to a charge of 0 in N2. And so if it's doing that, it's going from a charge of 4 negative to a charge of 0. And so because of that, it's releasing 4 electrons because it's going from a charge of 4 negative to 0. Or you can think of it as the fact like this is a charge of 0, this is a charge of 0, and now you have 4 H pluses there. In order to balance out the 4 H pluses to have an overall charge of negative, you have to add 4 electrons. Either way, it's the same kind of idea because it's really like working off of the idea that the H's each have 1 charge or like 1 positive charge each. So does that make sense first? How we did this and how I got just this right here. That reaction. Does that make sense? Any questions?
Yeah, that makes sense.
Okay. All right, so now we have our BrO3 negative that's being reduced. And so we have BrO3 negative, and we determined again BrO3 was carrying a charge because the oxygen had a charge of -6 here. The Br was holding a charge of +5, but now the Br is at a charge of -1. So that means that we've actually gained 6 electrons to get from BrO3 minus to Br minus. Okay, so we did that, and that's okay. But we have, so we can do BrO3 plus 6E yields Br minus. Okay, is everyone feeling okay on that part? You have BrO3, you gain 6 electrons, you get Br minus. Is that part of the reaction okay? Are there any questions on that?
You're gaining 6 electrons in order to make it like 0, right?
So it's so BrO3 negative had a charge, the Br was carrying a charge of +5, and then Br minus is a charge of -1. So it goes from +5 to -1. And that's why it has a charge of, that's why it has the 6 electrons. Does that make sense?
Okay, yeah, that makes sense.
Okay, so now that part, hopefully it's okay, where it's like, okay, Br had a charge of +5, it was going to -1, we need to gain 6 electrons for that to happen. Okay, fine. But the kind of confusing part is like, well, we had BrO3 negative, we had that O3 in there, we need to add that O3 back. But you can't, like, it didn't give you, the only ones that are not accounted for in these reactions are H2O, H plus, and OH minus. So normally you might be like, oh, can I just add OH minus because that's like the closest to O, and it'll like reduce the number of protons that we're adding. But we're in an acidic solution, so like you're not adding OH negative to anything here because it's an acidic solution, there's hardly any OH, and it would turn into water. And so that's the idea of like you're in an acidic solution, so in order to balance out the like the 3 oxygens on this side, we're gonna add H2O because we can't add OH minus because we're in an acidic solution. So okay, fine, I'm gonna add 3 H2O to balance out that. But now I have 6 more protons here on this side. Okay, well, to balance out the 6 protons that I just added on this side, I'm gonna add 6 protons here. So that's where this comes from. Are there any questions about that? Does that make sense?
Yeah, that makes sense. Yeah, that makes sense.
Okay, so now you have that. So now we're like, okay, let's compare these two. So you'd have N2H4 yields N2 plus 4H plus 4E minus. Yeah, that's all reactions, sorry. Then you have BrO3 plus 6H plus 6E yields Br aqueous and 3H2O. So we have 6E here and we have 4E here. We need these electrons to cancel out because we cannot have electrons in our final reaction here. And so in order to cancel these electrons out, we have 6 in one, we have 4 in the other. Our like lowest common multiple that we both will share, they both will share in order to cancel each other out is going to be 12. So in order to get there, we multiply this by 3. So we do 3 N2H4, 3 N2 plus 12H plus 12E minus. And then we do, so just basically this entire reaction is going to multiply by 3. Then this one, we need to get up to 12. So we're going to multiply by 2 just to get everything up to 12. But in particular, the 6 electrons up to 12. So if we multiply by 2, we're going to get 2 BrO3, 12H plus, 12E minus, 2 Br minus, and 6 H2O. And so, okay, our N2H4 is not going to cancel, neither is our BrO3, but our protons are going to cancel, and so is our electrons. And so our final reaction, I don't think it's here, but it should be 3 NH2H plus 2BrO3 negative yields 3N2 plus 2Br minus, and then you actually would have plus 6H2O on this side as well. I just need to include that. Are there any questions about that? Okay. If there aren't any questions, then it's past 4, so you guys are good to go. I'll upload the recording as soon as as soon as it loads, just takes a second to load. And then I'll also upload the worked out solutions and everything like that. Definitely feel free to send me an email with any questions you have as you study for the exam, and I'll try to respond as fast as I can tonight. But good luck. I'm sure you'll all do amazing on the exam. I think you guys have a pretty good grasp of the material here. Definitely try out the textbook problems if you want, if you all have access to the textbook. And if you want to just check answers or anything, you can just email me and be like, was number or whatever this value, and I can let you know. But good luck. You've got it. Feel free to shoot me any emails. But I think you guys will do great tomorrow. And I'll upload everything as soon as possible.